have completed the metal different types of defects, that is the stoichiometric and non-stoichiometric defects. In stoichiometric defects we have completed the vacancy defect, then interstitial defect, and in ionic solids the Schottky and Frankel defect. We also completed the metal excess defect in non-stoichiometric defects. Today we are coming with the metal deficiency defect. Metal deficiency defect. Now what is metal deficiency defect? In metal deficiency defect, metal ions will be deficient. That is, some metal ions, positions occupied metal ions will be vacant. For example, if FeO, iron oxide, is crystallized, iron has two oxidation states, Fe2 plus and Fe3 plus. These two ions are there for iron. So when FeO is crystallized, actually in FeO it is plus 2 state. So when it is crystallized, some positions will be occupied by iron having 3 positive charges, that is Fe3 plus ions. So instead of 3 Fe2 plus, Fe3 plus, this is Fe3 plus, sorry, Fe2 plus, Fe2 plus and Fe2 plus. See, the total charge is 6 plus. So when Fe3 plus is occupied, it can occupy only 2 positions, that is Fe3 plus, Fe3 plus, then 6 positive charges over. So 1 position is vacant. So more than Fe2 plus in the സ്ഥലത്ത് 2 Fe3 plus ne occupy ചെയ്യാൻ പറ്റുള്ളൂ. So that the charge is equal to plus 6. So one position will be vacant. One lattice site will be vacant. So if you take 100 atoms of 100 molecules of FeO, instead of 100 iron, there will be only 90. So the ratio becomes 0.98:1. So instead of 1:1, it became 0.98:1. That means the metal is deficient. Some metal ions sites occupied by metal ions are vacant. So this is metal deficiency defect. Another example is nickel oxide. Same case, nickel 2 and nickel 3. So the same case is there in nickel oxide also. So now we go to the another type of defect called impurity defect. Now what is impurity defect? See, when you add impurity to some crystals, some defects, some holes are produced, and you can make that crystal more conducting. So the defect created is called an impurity defect. For example, when sodium chloride is crystallized, if you add strontium chloride, we can create some holes. How? See, the positions occupied by sodium ion, sodium is having single positive charge, but strontium is having 2 positive charges. So when sodium chlorides, when some places lattice sites by sodium chlorides are vacant, and there if strontium is occupying, instead of 2 sodium ions, only 1 strontium can occupy, because to balance the charge. So 1 position will become vacant. So this hole can increase the conductivity of the crystal. So if sodium chloride, when it is crystallized, if you add strontium chloride, you can create impurity defect. Another example is when silver chloride is crystallized. If you add cadmium chloride as an impurity, instead of one silver ion, instead of the silver ion Ag plus ion, if cadmium ion is occupying, again you can create holes which will increase the conductivity of the crystal. 2 silver ions in the one cadmium ion occupy lattice site vacant. That a hole is created there. So like this we can increase the conductivity of such crystals by adding impurity. They produce cation deficiencies or cationic defects are produced. So this is impurity defect. Now we have completed all the different types of defects. Now next we will go to property of solids. These are the different types of properties. Properties of solids. First we will go to conductivity of solids. Conductivity of solids. Now, when you come to conductivity, solids are of three different types. They are good conductors, then insulators, and in between them there is semiconductors. Metals are all good conductors. Their conductivity range from 10 raised to 4 to 10 raised to 6 ohm inverse, Siemens inverse. This is the conductivity of ohm inverse, centimeter inverse. This is the conductivity of the metallic solids. Their conductivity is very high. If the conductivity is from 10 raised to minus 6 to minus 10 to 10 minus 20 to 10 raised to minus 10 ohm inverse, centimeter inverse, then it is an insulator. It is an insulator. So the conductivity is very low. This is a good conductor like metals. In between comes the semiconductors whose conductivity is from 10 raised to minus 10 to 10 raised to 4 ohm inverse centimeters. Then we call them as semiconductors. So solids are of three different types. Depending on the conductivity, we can classify solids into good conductors, then insulators, and then in between them there is semiconductor. Good conductors, the conductivity varies from 10 raised to 4 to 10 raised to 6. If the ohm inverse, centimeter inverse, then we call them as good conductors. If they are insulators, they have very low conductivity, and in between them there is semiconductor. Now, how can we explain this changes in conductivity of these type solids? Using band theory. What is band theory? This band theory is based on molecular orbital theory. Last year you have studied. All the atomic orbitals of having same energy merge with each other, or they combine with each other to form two different types of molecular orbital. Molecular orbital with a higher energy and molecular orbital with a lower energy. A set of molecular orbital with a high energy are called antibonding molecular orbital, and the set of molecular orbital having lower energy is called bonding molecular orbital. So when suppose there are thousands of atoms, metallic atoms, then or solid atoms will be there. The atomic orbitals, for example 1s1, so if it is 1s, all the 1s orbitals of atoms will combine to form 1s bonding molecular orbital and 1s antibonding molecular orbital. Then these 1s molecular orbitals are all joined because they are all having same energy. They will form one energy band. Then 1s antibonding molecular orbitals will form another energy band, and like that 2s, 2p, like that they will combine to form energy bands. The highest occupied energy band is called a valence band, and highest unoccupied energy band is called a conduction band. Now in metals, usually the conduction band and valence band either overlap with each other. For example, we will take the example of sodium, metallic sodium. It is 1s2, 2s2, 2p6, 3s1. This is the configuration of metallic sodium. 1s2, you will get a sigma 1s2, sigma 1s and sigma star 1s. All will be completely filled because all our atomic orbitals are completely filled. So molecular orbitals also will be completely filled. Then sigma 2s and sigma star 2s will be there. They also will be completely filled. 2p also completely filled. We come to 3s. This because all these are atomic orbitals are completely filled. Then molecular orbitals also will be completely filled. We come to 3s. We have one electron in 3s and one electron for another atom, and you get sigma 3s and sigma star 3s. Sigma star 3s. This is sigma 3s and this is sigma star 3s. and 1 plus 1 2, the 2 electrons will occupy in the bonding molecular orbital and the bonding molecular orbital will be vacant. Now all 3s and 3s sigma 3s orbitals will join together to form a valence band which is occupied. This is valence band and this unoccupied conduction band. This is the conduction band. Now in almost all cases for metals, this conduction band and valence band overlap with each other, or they will touch each other, so that the electrons in the valence band can easily jump to conduction band. So if the energy difference between the valence band and conduction band is very less, or if they are even overlap with each other, then that solid substance will be a very good conductor, so that electrons in the valence band can jump to conduction band. This is conduction band, and the energy difference between these two is called a forbidden band. It is called a forbidden band. In metals, this distance between conduction band and valence band is very less, or even they overlap. So they are good conductors. For insulators, the forbidden band is very large. That means there is a large difference between the conduction band and valence band, so that the electrons cannot jump to conduction band. Then that will be an insulator. For semiconductors, it comes in between these two, between the conductors and insulators. Insulators, the difference is lesser than that of an insulator, but it is larger than that of a metal. This is a semiconductor. So in semiconductor, if we add some impurity, or if you heat, that means energy of the electrons will increase, then they can jump to this conduction band, for example germanium, silicon, etc. If you increase the temperature, the electrons can get more energy, they can absorb more energy, and they jump to conduction band and their conductivity will increase. Such conductors are called semiconductors are called intrinsic semiconductors. Intrinsic semiconductors. Their conductivity will increase when you increase the temperature. When you increase the temperature, what happens is the electrons will get more energy and they jump to conduction band, their conductivity will increase. But for insulators, that is not possible. So this is a semiconductor, conductor and insulator, depending on or how we explain using band theory. So how the energy bands are formed? By overlapping of all the molecular orbitals having similar energies. For example, 1s orbitals, they overlap, they form 1s bonding molecular orbital and 1s anti-bonding molecular orbital. All the 1s molecular orbitals, sigma 1s molecular orbitals will be having same energy. They all overlap together to form an energy band. And they will be fully occupied. When you come to 3s, 3s is having only, in the case of sodium, 3s is having only one electron. So all the valence band will be completely occupied, and the conduction band, the outermost fully occupied band is called the valence band, and the unoccupied band is called conduction band. If the electrons can move to conduction band very easily, then we call it as a good conductor. How is a conduction band formed? All the unoccupied molecular orbitals will combine to form a conduction band. All the occupied bonding molecular orbital will form a valence band. So if the electrons can jump from valence band to conduction band, then that will be a good conductor. If they cannot jump, if the distance between the valence band and conduction band is very large, that is, this difference region in between these two is called the forbidden band. If that is very large, then the electrons cannot jump to conduction band, then it is an insulator. If it is in between these two, then it is called a semiconductor. And in semiconductors like germanium, if you heat, the electrons will get more energy and they can jump to the conduction band, increasing the conductivity. Then we call it as a semiconductor, and such conductors whose conductivity can be increased by increasing their heat or by heating, we call them as intrinsic semiconductor. We can also increase the conductivity of such semiconductors by adding impurities. For this process of adding impurity is called doping. To germanium, silicon, etc., whose valency is 4. If you add impurities, and the process of adding impurity is called doping, then we can increase the conductivity. We can add two types of impurities. First one, electron rich impurities. If you add electron rich impurity, then what happens? Electron rich impurity if you are adding. For example, germanium is having 4 valence electron. 4 valence electron is there for germanium. You are adding a 15th group element. Which are the 15th group elements? Nitrogen, phosphorus, arsenic, antimony, etc. Suppose you are adding arsenic to it. Arsenic is having 5 electrons. 5 valence electrons are there. Then what arsenic will do? It will come and take the place of germanium. And this what will happen? They will form 4 bonds with the neighboring atoms, but 1 electron is in excess. 1 electron is, you are adding arsenic and it has 5 valence electron, and then it will form 4 bonds with the neighboring atoms. 5th electron is free. That 5th electron will increase the conductivity of the silicon or germanium. We call it as such type of semiconductor. We call as N-type semiconductor. They are called N-type semiconductor. When you add an electron-rich impurity like 15th group element, who are having 5 valence electrons, 4 of them will form bond with the 4 neighboring atoms. In germanium, what happens is germanium is forming 4 bonds with the different atoms. In that place of germanium, we are adding arsenic. Arsenic atoms will occupy the place of germanium, and 4 electrons will form bonds with the 4 neighboring atoms. But the 5th electron, it will be free. That 5th electron will increase the conductivity. Such type of semiconductors are called N-type semiconductor, N for negative, N-type semiconductor. Now, if you are adding an electron deficient impurity, then what will happen? For example, germanium with a 4 electron. This is and each 4 electron will be forming, will be paired, or it is forming bond with the 4 neighboring atoms. This is germanium's crystal structure. Instead of that, if you add an impurity of 13th group, which are the 13th group elements? Boron, aluminium, gallium, indium, thallium, etc. Suppose we are adding indium. Indium has only 3 valence electrons. So instead of germanium, indium will take place there, and what happens is they form 3 bonds. But 4th, it is an electron deficient bond, because only 3 electron indium is having. This electron deficient bond is called a hole. The thing is, inside, if such a hole is there, the neighboring indium atom, neighboring germanium atom, there are 4 pairs. From this, 1 electron can jump to this hole, and hole will be created there. Then from here it can jump here, hole will be created here. So this hole can move anywhere. By electrons can jump there, and holes can be created. And this hole will be, as electrons will be jumping, but we feel as if the holes are moving. So this type of semiconductors are called P-type semiconductors. So N-type and P-type semiconductors are formed. So N-type semiconductor is formed if you add an electron-rich impurity like 15th group element. There, the impurity, when you add, what happens is that 5th electron will become more, will not be bonded there. It is free to conduct, so it will be conducting. If you add an electron deficient atom like indium, what happens is a hole is created. when a hole is created, indium can form only 3. It has only 3 valence electrons. 3 valence electrons will form bonds with the neighboring atom. The fourth place is free. That fourth is an electron deficient bond. Then this electron deficient bond is called a hole, and a hole is created. And this hole, what happens is the electron from neighboring bond can jump here, forming a hole there. Like this, the holes can move and increasing the conductivity of the crystal. This is called a p-type semiconductor. So n-type and p-type semiconductors are there. You can use the NP die. You might have as diodes. You can use them. Then, if one semiconductor is sandwiched between the other, NPN, PNP, etc., if such junctions can be used as amplifiers, etc., so they are all semiconductor devices. നീ ഇങ്ങനെ ഉറങ്ങി ഞാൻ